The James Webb Space Telescope, JWST, has just detected artificial light on the planet Proxima B, marking a groundbreaking discovery. JWST's MIRI instrument can detect large artificial light sources on distant planets, providing the first real evidence of the techno-signature of intelligent life forms. MIRI, a high-resolution infrared instrument, is very sensitive to infrared radiation and can detect distant major cities and industrial facilities from great distances. This feature extends not only to our neighboring system, Proxima Centauri, but also to possible alien cities throughout the known universe. This remarkable capability shows what we can achieve with advanced telescopes on Earth or near Earth. We can now detect large-scale settlements in the known universe after achieving a masterpiece with JWST's MIRI spectrometer. More exciting developments lie ahead, including the launch of the Very Large Telescope, ELT, in Chile in 2028, with its 39M main mirror deeper and sharper in space than ever before. These technical innovations are crucial because our thirst for knowledge about the universe is far from quenched. We are only at the beginning of our exploration of distant worlds and need instruments like JWST and ELT to study exoplanets for signs of life. Detecting artificial light from giant cities in space or alien airports is just one aspect. With the help of the ELT system, we will soon be able to detect traces of vegetation on distant planets. Such technologies will continue to evolve as we search for space for other species through advanced means until we find and connect with other life forms. The first detection of artificial light on Proxima B is a moment scientists have long dreamed of. For the first time, they will use a telescope to look at our neighboring star system so closely that habitable sites become visible. The artificial light source of Proxima B reveals the presence of technology and thus some form of advanced life. It may sound unbelievable, but JWST could even analyze our activities on Earth based on our light signatures. The best telescopes of all time can easily capture the lights of big cities like New York, Rio de Janeiro, or Beijing. With its fine sensors, JWST can filter the artificial light emitted by airports, large industrial plants, or even space stations from the Earth's natural light. That same capability has now been applied to Proxima B, providing a precise analysis of where life is located, how much artificial light it produces, and how mechanized the species is likely to be. This is a big step forward in the search for life in space, and one day we will surely have the technological means to communicate with other civilizations. If we wanted to send messages to Proxima B, it would take more than 4 years for them to travel in one direction in the normal way, and we would have to wait another 4 years for a response. Currently, all hopes are placed on the development of the first quantum computers. Quantum communication knows no fixed place or fixed time. Once we crack this technology, we will develop quantum communication tools and communicate in real time with distant civilizations. Although this may sound like pure utopia, utopias often become reality very quickly. In 2016, scientists dreamed of studying extraterrestrial worlds with the James Webb Space Telescope. The simulations were used to analyze the atmosphere and thermal properties of the exoplanet Proxima B. Scientists hoped to find out if Proxima B has an atmosphere that could be friendly to life. What was a utopia less than 10 years ago is now a reality. Simulations of Proxima B's unique orbit have revealed that this intriguing exoplanet is located in the habitable zone of its parent star, Proxima Centauri. JWST makes regular and deep observations of the day and night sides of Proxima B. This planet orbits its star in a locked fashion, just as our moon orbits us. Proxima B always has the same side facing the star, and the other side is always in shadow. Reconstructions have shown extreme temperature differences between the day and night sides of Proxima B, unless the planet has an atmosphere that redistributes the heat. Without an atmosphere, it would be hot during the day and freezing cold at night. The atmosphere would allow for a more even distribution of heat, which JWST can now study. Simulations in 2016 showed that there is a hard band at the boundary between day and night. It may seem strange to imagine civilizations living on a half-light, half-dark planet, with creatures living several thousand kilometers across the globe. However, it is possible. We must continue to open horizons and possibilities in the search for other life forms in space, and we need real analyses to be sure. In 2016, an accurate analysis of the chemical composition of Proxima B's atmosphere was still a dream. Today, JWST proves its ingenuity every day by providing accurate analysis profiles for worlds, sometimes hundreds or even thousands of light-years away. JWST recognizes the signatures of water, carbon dioxide, and methane, and has already made important discoveries. The latest comprehensive profile was obtained of the exoplanet K2-18b, where JWST found evidence of 4 biomarkers in the atmosphere. The more such biosignatures are measured around a planet, the more likely life may be there. Particularly interesting is the possible discovery of ozone, which is considered a strong indicator of biological activity because it is mainly produced by biological processes in our atmosphere. K2-18b may be an inhabited world, although no traces of artificial light have been found there. It may be a world of pure water, but that doesn't mean it's uninhabited. We have to consider that intelligent life in water, maybe even in cities, can exist, and not all advanced species can have artificial light. Humans were intelligent and mechanical in ancient times before the invention of the light bulb. JWST detects possible plant growth on Proxima B. Although it has not yet demonstrated its ability to detect plant growth on exoplanets, it has the potential to do so. Looking for life in space, we must rely not only on the technical characteristics and emissions of advanced species, but also look for planets that may only have plants and animals or other simpler life forms. JWST can provide indirect evidence of plant growth by analyzing atmospheric components and reflected light spectra. The researchers use MIRI spectroscopy, called vegetation red edge spectroscopy, which detects spectral signatures created by the reflective properties of plants in the infrared region. When light passes through an exoplanet's atmosphere and reflects off the surface, certain patterns in the reflected light can indicate the presence of chlorophyll or other photosynthetic pigments. Detecting such signatures is difficult and requires precise measurements and high resolution, which can be affected by disturbances in the exoplanet's atmosphere and the signal-to-noise ratio. Although JWST is designed for such measurements, we are just beginning to exploit these capabilities. Scientists are getting better at finding and identifying signs of life in space. We live in exciting times as JWST has started a revolution in space exploration. Direct detection of plant growth or biological activity will require future telescopes and missions specifically designed to look for biosignatures. One example is the planned LUVOIR, Large UV/Optical/IR Surveyor telescope, which aims to study the atmosphere of an exoplanet and identify possible biosignatures. Another important telescope under development is HabEx, Habitable Exoplanet Imaging Mission, which will take the first direct images of Earth-like exoplanets and analyze their atmospheres. Recent JWST observations have revealed a remarkable discovery: the detection of artificial light on Proxima B, a potentially habitable exoplanet orbiting Proxima Centauri. This breakthrough is a significant milestone in the search for extraterrestrial intelligence. Equipped with the MIRI
instrument, JWST demonstrated its ability to distinguish large-scale artificial light sources at great distances, providing compelling evidence of a techno-signature that suggests the existence of advanced civilizations beyond Earth. MIRI, JWST's high-resolution infrared instrument, operates with exceptional sensitivity to infrared radiation. Its capability extends beyond our local cosmic neighborhood, offering the ability to detect artificial light sources and perhaps even urban centers on exoplanets throughout the universe. This advanced capability positions JWST as a pioneering tool for exploring distant worlds and searching for signs of life outside our solar system. Looking ahead, the astronomy community is looking forward to making progress with the launch of the Very Large Telescope, ELT, in Chile in 2028. Equipped with a 39-meter main mirror, the ELT promises unprecedented clarity and depth when observing cosmic phenomena. This next-generation telescope aims to push current observational limits and provide better opportunities to study exoplanet atmospheres and potential biosignatures. The quest to understand distant worlds and possible extraterrestrial life remains at the heart of modern astronomy. Instruments such as JWST and future telescopes such as the ELT will be central to this effort, enabling detailed analysis of extraplanetary conditions and environments. The development of new technologies, including quantum computers and advanced space observatories, promises to transform our ability to explore and communicate with extraterrestrial civilizations. The discovery of artificial light from Proxima B underscores the transformative impact of space telescopes in unlocking the mysteries of space. These telescopes will not only expand our knowledge of distant planets and the composition of their atmospheres, but will also pave the way for potentially groundbreaking discoveries in astrobiology. By detecting signs of technology and analyzing spectral data, astronomers can infer the existence of advanced civilizations and get an idea of their technological capabilities. In addition, space exploration has the ability to identify and analyze vegetation on distant exoplanets.